Let's look a little bit about the structure of matter, how matter is made up. So what's the smallest amount of a substance you need in order to call something this is the substance of water? You might think it's an atom, but if you think about water, say, it's H2O, we all know that, right? So which atom would we consider? Hydrogen or oxygen? Right, so you need to consider the molecule. That becomes immediately obvious. You need two hydrogens and an oxygen sitting at a certain angle, right, bonded together at certain angles in order to make up one molecule of the substance. So you need at least one molecule to form water. Yeah, that's what matter is made up of, molecules. Okay, and some matter, like for example, if you have pure gold, then you just need the atom because all of it is made up of atoms of gold. Yeah? You don't have a gold molecule, in which case an atom would suffice, but normally you need a molecule. Okay? Molecules themselves are made up of atoms corresponding to the elements required. So what is the atom? We talked a few minutes ago about the atom having a nucleus, which is very dense. So you have a small nucleus, inside which are the heavy protons and neutrons. Neutrons are neutral particles which have the same mass as the proton. Proton are positively charged particles. So if you just have the nucleus, it's positively charged. Okay? You need to balance this in the atom. So you have an equal number of electrons, which are rotating in orbits, and they're negative charges. Electrons are extremely light, okay? So they have almost no mass, very, very negligible mass. So most of the mass of the atom is inside that smaller nucleus. The orbits hardly carry any mass in them, okay? That's the fundamental structure of the atom. So if you have a gold bar and you break it down into half and half and half and half and half, and you keep halving it, at some point, you will come down to the atom, right? And if you stick this bar under a microscope that can actually look at the atoms, then what you will see is a regular array of gold atoms. So each of these, the orange inside and the light brown outside, forms one atom. Here we have several atoms in an array that we might call a lattice. Okay, so they're arranged in a regular order. And if you look inside the nucleus, which is the orange nucleus, there are actually two types of particles. We have the gray neutrons and the red protons, or the orange protons. Okay, so that's going further in, smaller. And if you look inside the neutrons and the protons, you actually have what are called quarks. And there are 6 types of quarks. You can have up, down, and different names for the quarks are there. It's not important for you to memorize those, but quarks have different spin and they have to be balanced so that you can form the right thing. So you might have 3 quarks making up a proton, or 3 quarks making up a neutron, okay? So this is as far as our knowledge goes today. We do not know whether the new quarks are made up of something further smaller than this. And that's the work of particle physicists. Okay, so particle physicists study these particles and how they interact together. That's the work that Feynman did in his string theory. Okay, one of the best physics teachers ever. So that was just to give you a little flavor of the structure of matter. Now we come to dimensional analysis. Okay. Dimensional analysis is a tool that physicists like to use, and essentially it checks for the correctness of a formula or an equation that you may have. Okay. So it can definitely check that something is incorrect. It cannot tell you that something is definitely correct. Okay. Essentially what we do is we use the dimensions which we learned before, mass, length, and time, and we need to combine them an algebraic ways, just like multiplication, addition, subtraction, division, like you do in algebra, okay? And we'll see examples of this in a minute. If you have an equation, both sides of the equation need to have the same dimensions, that means the same powers of m, l, and t, in which case this is a plausible equation. It doesn't say that this is a correct equation, that it exists, but it's plausible. Whereas if your left-hand side and your right-hand side dimensions do not match, then it's definitely incorrect. This equation cannot exist. And that's what it checks for, the correctness of an equation. So let's do a simple problem on this. Show that the expression v equals v naught plus at is dimensionally correct. Okay. Now, obviously, you haven't come across these terms, so I'm going to explain these to you. V is velocity. V0 is velocity at some initial time 0. A is acceleration, t is time. Okay. So velocity you could consider like speed. Okay. For now, so its dimensions are going to be what? We often measure it like miles per hour. So you have something like a length unit divided by a time, right? So our dimensions for velocity, we're writing it in square bracket. That means we're writing about the dimensionality only. Okay, so v and v0, which are both our velocity dimensions, they're going to be L divided by t, length over time. So we've got two terms by thinking about this. What about acceleration? Acceleration is the rate of change of velocity. So we need to take our velocity and divide it by another time. So we have length per time squared as the dimensions for acceleration. For time, we just have time as our dimension. We can cancel these two. Remember I said it's algebraic. So we cancel the square term with the t here. We get L over t. So this on our left-hand side, we have L over t equals L over t plus L over t. We can add the two L over t's. So both sides are L over t. The fact that you have two L over t here does not matter. A number, an integer does not matter. Okay? Exponents matter, but whole multiplications do not matter. So we have the dimensions of L, t to the power negative 1, m to the power 0, if you like, and the same on the other side. Hence, you can prove that this equation is dimensionally correct. Okay?